Hey, this is Josh from LeetDev, where we explain programming questions as simple as we can. Today, we'll be talking about the longest consecutive sequence problem. In this problem, we're given an unsorted array of integers, number, and we want to return the length of the longest consecutive element sequence. What does that mean? So in example 1, we're given a sequence of these numbers, and the longest consecutive elements is 1, 2, 3, 4, and therefore the length is 4. And then in example 2, we're given this sequence of numbers, and the length is 9 because we have 0, 1, 2, 3, 4, 5, 6, 7, 8. So as you can see, we're just looking for a string of numbers that are just one higher than each other. A follow-up to this question is that we want to solve this problem in O of n time. The first way to solve this problem is to sort the array. Because the problem wants us to find the longest sequence of characters that are consecutive to each other, then if we sort it, we can easily iterate through our array and then find all the sequences. After we have sorted our given array, we now have this array in front of us. All we need to do now is just scan our array, and we would find one sequence over here of length 4, one sequence just at 100, and another sequence at 200. And so this would be our longest string. The runtime of this algorithm is O of n log n, because the act of sorting itself is n log n, and then scanning through the sorted array is a linear operation. The spacetime complexity of this algorithm is O of 1, or the O of n, depending on your sorting algorithm. But assuming it's in place, it's O of 1, because we're not using any extra space to sort or scan through our array. The follow-up question wants us to solve the problem in O of n time, which unfortunately means our sorting solution does not work. To solve a problem in n time, that means we need to only linearly scan through our array to see if we can find an answer. One insight from our linear solution is that it basically placed all of the values that are in sequential order next to each other, and so we can just do a quick O of 1 lookup. However, is there any other data structure and algorithm that we can use to achieve that same effect? Why, yes, there is, and that is a set. By placing all of our values in a set, we can then quickly look and check to see if a i+1 value exists in constant time. Similarly to how we would just check the next index of our sorted array to see if the next number is part of our current sequence. The first thing we do is we would store all of our numbers in a set. And once we have the set, we can easily check to see an existence of a number. Now, skip step 2 because this is an optimization. We'll go to step 3, and we're going to count all the sequences from our starting index, and then we'll increment that value by array plus 1 until it's no longer in the set. So an example is that, let's say we start at 100. We have a length of 1 for 100, and we can quickly check to see if 101 exists in our map, which it doesn't. And so we have 1 there. 4, same situation. 200, same situation. And then once we arrive at 1, we can quickly check to see if there's an existence of 2. We see that it does exist, so then we have length of 2 now. And then from there, we can quickly check to see if there's an existence of 3. And there is. And so we continue and check if there's 4. And then we finally check to see if there's 5, which doesn't exist. And then once we reach 3, we would do the exact same thing. We would check to see if 4 exists, and so on and so forth. By doing this, we'll have a runtime of O of n squared, because potentially, let's say we have an array of 0 through 5. That means for every single n element, we need to check a n minus 1 element, and that would give us a n squared solution. However, one way we can optimize this is that instead of searching for a sequence in every number we encounter, we can just look for numbers in our array that's value minus 1 does not exist. By doing this, we now guarantee that at most we would scan through our elements n plus n times. For example, in an array from 1 to 9, we would scan through it n times because we would start at 1, which is our lowest sequence value, and then we go all the way to 9, and then we would scan it another n times to look for other sequences, which we don't find. n plus n will give us 2n, which is amortized to O of n. Now the trade-off for being able to use the set is we would have a space-time complexity of O of n, because now we need to use a set to store all of our numbers. We first start by defining our set. In our algorithm, we want to store everything in our array in our set. Then once we've done that, we need to set our max answer that we need to return. So now we can start implementing our algorithm. What we want to do is we want to iterate through all the numbers in our array, and then check in our set if the current value we're at, -1, exists in the set. If it does exist, that means that the current number we're at is in a sequence of another number. And if it's not, that means the current number we're at is the start of a sequence. And when that happens, we just check to see if the next element is in the set, and we just continue incrementing until we've reached the end of our sequence. So let's go through our problem. We start off with a value of 0 for our max number, and then we start at the first index in our array that we're given. So at 100, does 100 minus 1, 99, exist in our set? No, it does not. So that means we found the start of a sequence. We set our current streak to be 1. And then we check to see if 100 plus 1 exists in our set, which in this case it doesn't. So we don't increment our count. And then we check to see if our current streak is larger than our max, which it is. So we update our value. And then we check the next value in our array. So at 4, we check to see if 3 is in our set, which it is right here. That means we don't do anything and we skip 4. And then we go to 200. 200 would be the exact same as 100. We would have the longest sequence of 1. And then we go to 1. 1 minus 1 is 0, and 0 is not in our set. So that means we can start going through our sequence again. We set our current number to be 1 and our current length to be 1, which is just our value by itself. And we check to see if 1 plus 1 is in our set. It is. 2 is right here. And so as a result, we can update our current value now to be 2. And then we can update our longest sequence to also be 2. And then we repeat our while loop until it's false. So it's 3 in our set, it is. Update our current sequence to 3. Is 4 in our set? Yes, it is. So we update our current sequence to be 4. And then finally, 5 is not our set, so we need to update our max to be the larger of our current or max's previous value, which currently is 2 versus our current 4. So max is now 4. So back at our 1, we move on to the next index in our array, which is 3. 2 already exists in our set, so we move on to 2. 2 minus 1 is 1. 1 is in our set, so we don't do our algorithm again. And then finally, after we finish iterating through all of the numbers in our array at O of n time, we just return our max value, which is 4, and is the answer to this question. Now let's submit and see how we do. And there you go, and this is how you solve the longest consecutive sequence problem. There's another interesting variation to solve this problem. We used a hash set to instantly look up the next number in the sequence. However, this problem is also a great example of a union find algorithm. If you're interested in more in union find or how to solve this problem in union find, leave some comments below. Otherwise, if you found this video helpful, consider hitting the like button and maybe even subscribing for daily updates. Otherwise, I'll catch you in the next video and have a great day.